Okay, the final part of this lecture series involves simplification of the force and couple system. Up to this point, we actually studied about the force system, the moment system, the couple system, and if you notice, the more external load acting on the body, the more complex your calculations become. Kan? Daripada setengah muka surat jadi satu muka surat, jadi satu buku, it becomes incomprehensible. So, in this particular video, we are going to look into how we can simplify the force and the couple system into manageable free body diagrams. Most engineering structure involves multiple forces and moment system acting on a body. For example, along the beam, there's a tension cable, there's a traffic light there, and there's two Spiderman hanging out on a beam. Tiba-tiba, macam tak ada tempat lain pula dia nak lepak Anyway, if we convert all the external load into force vector lines like this, so we can see that there are multiple external forces acting on the beam. Such forces may also create moment at certain points along the beam. The computational process may be a bit complex when involving different forces with different direction at different points. Well, good news. Such system can be simplified by shifting all the resultant forces and moment to the support point at the origin. Okay, so you can actually calculate the resultant forces and moment at a single point instead. Okay, let's look at this example. In this example, you are required to interpret all the external force into an equivalent single forces at point O. Okay, so if I were to label all the external forces acting on the body, there is 1, 2, 3, and 4 external forces acting on this particular beam at various directions. Compared to all the other forces, only F2 yang sengit je kan. So, in order to ease your calculation, you can actually resolve F2 into X direction and also into the Y direction. So, using the trigonometric function, I can find the magnitude of F2X, which is equivalent to the magnitude of F2, which is 500 Newton multiplied with cos theta. So cos theta in this case, kalau tengok this little triangle over here, would be sebelahan 3 over 5. Okay, so the corresponding magnitude would be 300 Newton. So correspondingly, you can also find the magnitude of force 2 along the y direction by you multiply the force of 500 Newton with sine theta. So sine theta in this case is 4 over 5, and you will get a corresponding magnitude of 400 Newton. Okay, now that all the external forces are appropriately described in either x and y direction, we can easily find the resultant forces. Okay, so let's solve for the x direction first. So if you want to find the resultant force along the x direction, so let me just highlight all the forces acting in the x direction, which is this one, F2x, F3, and also the F4. So we can calculate the summation of the resultant forces along the x direction, and we assume that the rightward direction is positive, then the total would be F2x, which is positive 300 Newton, rightward direction, so it's positive, and then minus the 200 Newton from the F3 and plus with the 200 Newton from the F4. Okay, so follow the direction of the forces accordingly. So the magnitude of the resultant forces along the x direction would be 300 Newton. Because it's positive, meaning this magnitude is to the rightward direction. Okay, and now you repeat the same step along the y direction pula. So assuming the upward direction is positive, let's identify the forces acting in the y direction. Okay, there are two forces in the y direction, which is this one and also this one. So the 750 Newton is pointed downward, so you can write it as negative 750 Newton. And then the F2y is pointed upward, so you can write it as positive 400 Newton. And you will get a corresponding magnitude of negative 350 Newton. So this magnitude can also be rewritten as 350 Newton, and because the magnitude is negative, it means that the direction of the resultant force along the y-axis is downward. Okay, now the next thing we need to look for is the resulting moment acting at point O. So this resulting moment is caused by all the external load acting on the beam. As for the moment calculation, assuming the counterclockwise direction as positive, then the summation of the moment along the O axis or point O be equivalent to summation of all the forces multiplied with the perpendicular distance to the point O. Okay, so there is 750 Newton over here, and the perpendicular distance to point O is 1.25 meter. Okay, so if you draw an imaginary circle around point O, then you will get the direction of this moment to be in clockwise direction. So if it is in clockwise, then the magnitude of this particular moment will be in negative. So the second force over here is 400 Newton, and then you have to multiply it with the perpendicular distance to the line of force to the point O. So in this case, the D would be 1.25 plus another 1.25. And again, if you draw the imaginary circle around point O, you will find that the direction of this particular moment to be in counterclockwise direction. So it will be positive. Now the third force acting on the body is this one, which is 300 Newton. Again, accordingly, you have to multiply it with the perpendicular distance. So the distance in this case would be 1 meter. So if you draw an imaginary circle around point O, you find that the direction of moment caused by this force to be in clockwise direction. So the magnitude of the moment is negative. Okay, now if you look carefully at the F3 and F4, it have the same magnitude with the opposite direction. So it's actually a couple force. So you can calculate the moment of this couple force by multiplying the magnitude of the couple force with the perpendicular distance between the forces. So in this case, your calculation becomes so much simpler, whereby the moment for this particular couple will be equivalent to the force of 200 Newton multiplied with the perpendicular distance between the couple force, which is 1 meter. So how about the direction of the moment caused by this couple force? So again, you draw an imaginary circle connecting between these couple forces, and you'll find that the direction of the moment to be in counterclockwise direction. So the magnitude of this moment is positive. So the expression at the end of this equation is specifically for the couple moment. So you total up all the magnitude over here, and you get a corresponding magnitude of moment to be negative 37.5, and the unit would be in Newton meter. So this particular expression can also be rewritten as 37.5 Newton meter, and because it's negative, it means that the direction is in a clockwise direction. All this calculation simply means that all the external forces acting on the body can actually be simplified at one point, which is point O. So we know that the resultant force in the x direction is 300 Newton. So we can redraw it in our picture like this. So the direction is to the right and the magnitude is 300 Newton. Okay, so we also know that the resultant forces in the y direction is 350 Newton. But the direction is downward. Okay, so this is how it looks like. Okay, correspondingly, we also know that there is a moment at point O with a magnitude of 37.5 Newton meter in clockwise direction. Sebenarnya, I can actually further simplify this magnitude by finding the resultant moment of the external forces acting on the x and also the y direction. So you know that the calculation of the resultant force is equivalent to Frx squared plus Fry squared and then square root all the summation. So if you substitute all the values into your equation, and you will get a corresponding resultant force to be 460.97 Newton. So the direction of the resultant force would be somewhere in between the x and the y forces. So in this type of direction, it's more appropriate if we find the angular displacement of this particular force. So if I were to extract this particular triangle over here, it becomes a trigonometric triangle. The theta would be over here, and the magnitude along the x direction would be 300 Newton, and the magnitude along the y direction would be 350 Newton. So you can actually calculate your theta or the direction of your resultant force by using the trigonometric function, whereby tangent theta is equivalent to opposite divided with next weight, which is 350 Newton, divided with the 300 Newton. So the corresponding magnitude of your theta would be 49.4 degrees, and the magnitude would be over here. Now let's look at another example on how we can simplify the force and the moment in a 3D system. So let's look at the strategy in solving this kind of problem. You know you need to find the resultant force at point O, and you also need to find the resultant moment also at point O. So let's look at how many forces are there in the 3D system. There's F1 over here and there's F2 over here. So you have to convert the magnitude of F1 into a vector form, and also you need to find the vector form of F2 as well. Okay, so how about the moment? So you know the moment are being produced by this M over here, and then there's also external load acting on the beam. So that external load will also create moment force. So you also need to find the moment caused by force 1, or we call it M1, and the moment caused by force 2, and we call it M2. So correspondingly, for the resultant moment, you need to find the vector of M and the vector for M1 and also the vector for M2. So these are the items that you need to find in order to get the resultant force and also the resultant moment. So let's find the vector expression of F1. So you know the magnitude of F1 is 800 Newton, and the direction of F1 is only moving in the Z direction. So this is quite straightforward. So you, in a way, you know that the vector of F1 would be negative 800 because it's pointed downward in the K direction. Okay, and the unit for this vector is Newton. Dah siap. The next thing we need to look for is the vector of F2 pula. So we know F2 lies within the Y and also the X plane. Unfortunately, the theta or the angle over here is unknown. So we can also find the vector of F2 by using other formula. If you could recall, the vector of F2 can also be calculated by multiplying the magnitude of the force with the unit vector of that particular line. So in this case, the unit vector that we are interested in would be the unit vector of point CB. Also recall from the previous lecture series, the unit vector can also be calculated by dividing the position vector of CB with the magnitude of the position vector. So based on this relationship, let us find the value of the position vector. So remember, position vector is closely associated with the respective coordinates of that particular point. So the position vector of CB would be equivalent to the position vector of B minus with position vector of C. So position vector of B can be attained by identifying what is the coordinate of point B. So if you look at this picture, the coordinate of point B would be negative 0.15 in the X direction. Okay, look very carefully at the punya direction tu ya. And then along the Y direction, it would be 0.1, and along the Z direction, it would be 1, and the magnitude would be in meter. Okay, accordingly, you can also find the coordinate of point C, whereby along the X direction, it will be 0, along the Y direction is 0, and along the X direction is 1. So based from these coordinates, we can easily convert it into an equivalent vector form, whereby the vector of RB would be negative 0.15i plus 0.1j plus 1k, and minus with position vector of C, whereby in vector form it would be 1k. Okay, you simply solve this equation and you will get a corresponding vector of negative 0.15i plus 0.1j. K dah terhapus lah dekat situ. So, the unit of this position vector is in meter. So, from this position vector, you can calculate the magnitude of the position vector simply by kuasa 2 of negative 0.15 squared plus 0.1 squared and then square root all the summation. So the corresponding magnitude of this position vector is 0.1803 and the unit is again in meter juga. So going back to our main intention, we want to find the vector of F2 kan. So F2 is equivalent to magnitude of F2 which is 300 Newton multiplied with the unit vector which is dividing the position vector of CB with the magnitude of the position vector. Okay, if you solve this calculation, you will get a corresponding vector to be negative 249.58 in the direction of I plus with 166.39 in the direction of J. And the unit of this vector would be in the form of Newton because force kan. So our F2 is done and this particular section is the calculation involved when finding the force vector. So the next step is we want to find what is the moment vector. So the next thing we want to find is the vector of moment 500 Newton meter here. So if you look carefully at the direction of this particular moment, it lies within the y and the z plane. So you can actually resolve the magnitude into y direction by which you can calculate using the 500 multiplied with cos theta which is 4 over 5 Newton meter, and the moment in the direction of z can also be attained by multiplying 500 Newton with sin theta which is 3 over 5 Newton meter. Going back to our moment equation, we can actually rewrite our vector in the form of negative my in the j direction. Jangan lupa negative because it's in the negative y direction. And then plus with magnitude of moment in the z direction. Tapi z tu you replace dengan k hat. Okay? Use the value that we defined earlier whereby my is 500 multiplied with 4 over 5. So that is the magnitude in the direction of j, and mz is equivalent to 500 multiplied with 3 over 5 in the direction of k. Simply solve for this calculation and you will get a corresponding vector of negative 400j plus 300k, and the unit for this vector is Newton meter. Ingat ya, because it's moment. Based on our checklist, the vector m is done. So the next thing we need to look for is the vector m1. Now, if you look carefully at the figure given, the force 1 passes through the rotation point O. So you know from previous exercise, any forces which passes through the rotation point or the rotation axis would not create any magnitude of moment. So the moment 1 would be 0. Okay, so dah siap. So the third item that we need to look for is the vector of m2 pula. M2 is the moment caused by force 2 over here. So if you look at the direction of the force, if you recall from the previous lecture, the vector of moment can also be calculated by using cross product, whereby you need to cross product the position vector connecting between the rotation point to the line of force with the vector of the force itself. So you need to find RB cross product with F2. So again, when using cross product, it is more convenient to express it in metric form. The first layer would be the IJK direction, and then the second layer would be the respective magnitude in the position vector of B. So remember vector B tadi kita dah kira, which is this one. So you just rewrite the magnitude over here. The third layer would be the magnitude in the F2 vector. So again, you place all the magnitude accordingly in your metric form. By this time, I think all of you dah terror dah to solve the cross product on your own. Anybody having any problem, please DM me, ya. Okay, so you will get a corresponding moment vector to be negative 166.39 in the direction of I, minus 249.58 in the direction of J, and negative 0.0005 in the direction of K. So that is the vector of your moment caused by force 2. And don't forget to include the unit of your moment to be Newton meter. So all this calculation in the red colored font is the corresponding moment vector that we need to find. So the next step is you can find the resultant forces based on the values that we attained earlier. So the resultant force is the summation of the forces over here. So we need to sum up vector force 1 plus with vector force 2. So you just rewrite the vector expression that you calculated earlier, whereby the force 1 is this one, which is negative 800k, and force 2 is this one. So we'll just rewrite it, negative 249.58i plus 166.39j. So you'll get a corresponding resultant force of negative 249.58i plus 166.39j minus 800k. So this is the force vector of all the forces acting on the beam. Now the next thing you need to look for is the resultant moment, where it is the summation of moment m, m1, and also m2. So the step here is quite straightforward. You just rewrite all the vector of the moment that you have calculated earlier, which is the vector of m, vector of m1, and also vector of m2. So yada yada yada, you try to kira on your own and you will get the corresponding resultant moment to be negative 166.39i minus 649.58j plus 300k. And then don't forget the unit of the resultant moment is Newton meter. Okay, so dah siap. What it means by this calculation is that all the forces and the moment which is acting at different point of the beam can also be represented as the resultant force and moment at point O. So kalau you draw the direction of the force, you follow the magnitude of the Cartesian vector tu accordingly, and this would be the direction of your resultant force. Okay, accordingly for the moment axis pun you boleh identify what is the direction based on the vector of the moment. Okay, so you rewrite it again, sketch it again, and this would be the direction of your moment. Okay, that is all for now. I hope you enjoy the lecture series and enjoy the PKP season at your place. So, in the next lecture, we are going to look into the more in-depth topic of engineering mechanics involving equilibrium of a rigid body. So, till then, see you later, alligator.